Let's look at, this is the mock AP exam number 2 for 2020. This is number 1, the extended FRQ problem that's meant to be 25 minutes long. So we have a bit of Riemann sums here. Table of values. Two particles move along the x-axis. Particle Q's position, velocity, and acceleration are given in a table below. So we have the position provided by Q of t, Q prime gives us velocity information, and Q double prime, or acceleration. These values are acceleration values. And then we have a separate particle. Particle P has a velocity that's given by this piecewise function. So we have two particles with different sets of information provided for each. Part A, find the average acceleration of particle Q. So we're going to look at the table here. The definition for average acceleration is change in velocity over change in time. So notice that when we do average acceleration, we don't touch acceleration function. It's not change in acceleration over change in time. That's something else. All right, so average acceleration, the definition of acceleration is change in velocity over change in time. So we find our velocity at the endpoints, v of 10 minus v of 0 over 10 minus 0. So our v of 10 is 4, right? V of 0 is 2. So 4 minus 2 over 10 minus 0, we get average acceleration being 1/5. Part B, for particle Q, okay, we're still on particle Q. Explain the meaning of the definite integral 0 to 10 absolute value of v of t dt. So we're basically accumulating velocity over a period of time, but the absolute value indicates that this is not displacement, this is going to be total distance traveled. So even if particle Q is moving forwards and backwards, we're counting all the backwards backwards motion as a positive value. So the way we interpret this with the absolute value is that this definite integral represents the total distance traveled by particle Q in the time interval from 0 to 10. Okay. Now we're going to approximate the value using trapezoid approximation with 3 subintervals indicated in the table. So we're going to go from 0 to 10. We're going to separate these out so that each subinterval sees the same number of order pairs, and make sure that when you do Riemann sums that you're overlapping each of your subintervals. Okay, overlapping at the 2 and at the 6. So the formula for trapezoids is width over 2, height 1 plus height 2. Okay. But we have to make another adjustment, is the fact that the absolute value indicates that when we pick out the heights, if we see any negative heights, we're going to have to change them to be positive. So if the negative 1 is going to be adjusted, the negative 2 is not going to be used as part of our subinterval y values. But for the first one, to be width over 2, so 2 over 2 times 2 plus 0, 4 over 2 plus 0 plus 1 times 0 plus 1, and then 4 over 2 times 1 plus 4. So our total distance using trapezoid approximation is going to be 14 units. Okay. For part C, for particle Q, evaluate the definite integral from a to t and explain the meaning of this value. So the integral from 0 to 10 of acceleration, we're not going to use any approximation, we're going to find the actual value of this, and the way we can do that is we can apply first theorem. So first theorem says we can take the antiderivative, bring it up one level, and then plug in upper and lower bound. So integral of a of t is just v of 10 minus v of 0. Now if you're trying to use trapezoid approximation or any other Riemann sums, then you're only getting an approximation. Here we are actually getting the exact value using this formula. So v of 10 minus v of 0 represents the change in velocity in the time interval from 0 to 10. Okay. So when we evaluate this, v of 10 is going to be 4. And then v of 0 is going to be 2. So the integral from 0 to 10 of a of t dt is going to be equal to 2. All right, part D. At t equals 1, are the particles p and q speeding up or slowing down? Show work to justify each answer. So to determine whether the particles are speeding up or slowing down, we're going to have to compare velocity and acceleration. Okay, compare signs of velocity and acceleration. So at 1, we can just pick out information from our table for particle q. So velocity at 1 is going to be 2, and acceleration at 1 is going to be -1. And then for velocity, for particle p, what we can do is we can plug 1 into the velocity function, and when we do that, it will be because p represents the velocity, so we can plug 1 into the velocity function. We get 3 plus 2 minus 1, which is 4. That's positive. If we plug 1 into the acceleration function, which will require us to get from p to p prime, and we can take the derivative of each of these functions. Okay. And then again, it's going to be with the first piecewise for p prime. Plug 1 in, we're going to get 0, and they don't fulfill the condition of either same signs or different signs. So particle q is neither speeding up nor slowing down because it doesn't match those conditions of same signs or opposite signs. Now for particle q, I think I meant to say 3 and -2 instead of 2 and -1. So at 1, we should get 3 and -2. Okay. So let me change that. 3 and -2. So we're still getting opposite signs. So particle q is slowing down since signs of acceleration and velocity are opposite. All right, for E, find the limit as x approaches 3 from the left. And if we want to find the limit, first thing we do is we always plug in our x value. So let's plug in 3 in for all the x's that we see. Okay. And I meant for this to be t here. So as t approaches 3. So we plug 3 in for all the t's. And we're going to get 1 minus e to the 3 minus 3 over 2 times p of 3. And p of 3, we can look at our piecewise function. P of 3 is simply going to be plugging into the first piecewise, so 3 plus 2 times 3 minus 3 squared. That will give us 0. The numerator also gives us 0. E to the 0 is 1. 1 minus 1 is 0. So we get 0 over 0, which means we can apply L'Hopital's rule. So L'Hopital's rule, we can find the derivative of the numerator and denominator portions. So numerator, 1 goes to 0. E to the 3 minus x becomes e to the 3 minus x times -1. Denominator, p of t becomes p prime of t. Okay. We reevaluate, plug 3 into the remaining variables, and we get e to the 3 minus 3 over 2 times 2 minus t, because 2 minus t is the derivative of p within this interval. And when we do that, we get 2 times -4, which is -8, so 1 over -8. Okay. All right, moving on, last two here. Let h represent q of t over 3 minus t squared. Find h prime of 1. To find h prime of 1, we first have to find the derivative. To find the derivative, notice that this is set up as numerator and denominator. We have to go through quotient rule. So we can say f prime times g minus f g prime all over g squared. So f prime, we take q, find the derivative, becomes q prime. Denominator, 3 minus t squared. The original numerator, q of t, denominator's derivative, 3 minus t squared becomes -2t, that 3 goes away to 0, all over denominator squared. We have our derivative. Now we can re-evaluate, replace all the t's with 1, and now we can make our substitution. So q prime of 1, we look at our table of values, is going to be 3. And then q of 1 is going to be 7. And once we clean everything up, we get 6 plus 14 over 4, which reduces to be 20 over 4, which is 5. Part G, do particles q and p both change directions in the interval from 0 to 4? Show work to justify your answer. So if there is a change in direction, there has to be, we have to first find out if there's a place where there's a velocity 0, and then from there we can determine if there's a change in signs, change in directions on either side of that critical value. So for for a particle p, we can take our velocity function and we can set equal to 0. And when we set equal to 0, we can factor -1 out, solve for t, we get -1 and 3, and so we found a critical point there. Okay, we don't, even though p of t only extends from 0 to 3 for the first piecewise, the second piecewise, we know that this is not going to equal to 0 from 3 to 4, so we don't have to worry about any critical points there. So then we just test, is there a change in sign? So if we plug 1 into the first piecewise function, we're going to get 3 plus 2 minus 1, which is positive. And if I plug 4 into the second piecewise, I get 2 times 4 times e to the 2 minus 4. That is also positive. So we see that there is no change in signs, therefore there's no change in direction, and there's no change in direction for particle p between 0 and 4. Now for particle q has at least one change in direction in the interval from 0 to 4. Okay, and the reason why is by intermediate value theorem, we have velocity that is positive and then changes to velocity that is negative. So even though we don't know exactly where there is that exact t value where there's a change in direction, we know that because the function is continuous and it has to transition from a positive to negative somewhere, and we see that's the case with particle q. So if we look at particle q and we look at the signs here, we see that there's a positive velocity, it goes to a negative velocity, so we know there must be a change in sign. Maybe there's more than one, maybe it's at 2, maybe it's at other points, but that transition tells us there must be a change in direction somewhere between, because this is a continuous function. And then second, from -2 to -1 to 4, we know there's another change in direction there. Okay.